Hi again, it's Mrs. Scarpel, and in this video we're going to take a look at, well, how can we use X and Y intercepts in an application? So here is an example of an application problem. You are going to the fair and you have $16 to spend on rides and games. Ride tickets cost $4 and game tickets cost $2. The equation 4x plus 2y models this situation where X is the number of ride tickets you buy and Y is the number of game tickets you buy. Find the intercepts and interpret their meaning. And we're going to be interpreting their meaning because this problem has context to it. So let's start with that x-intercept. Remember, to find the x-intercept, it's when y is 0. So we're solving for the x when y is 0. So not another 4, I want a 2. So 4x plus 2 times 0 equals 16. So we have 4x equals 16. Divide both sides by 4. And we have x equals 4. And we said X is the number of ride tickets. So we can buy 4 ride tickets if we don't, I was going to say when, but I'm going to use if we don't buy any. What are the other tickets? Game tickets. So X is 4 ride tickets if we don't buy any game tickets. Let's find the y-intercept. Again, the y-intercept is when X is 0. So we have 4 times 0 plus 2y equals 16. So basically 2y equals 16. Divide both sides by 2. And we have y equals 8 game tickets if we don't buy ride tickets. So when you're asked to interpret the meaning, this is what we're saying. We're giving a reason why we have 4 ride tickets. We have 4 ride tickets because we aren't buying any game tickets, or we have 8 game tickets because we aren't buying any ride tickets. Now we're going to graph this equation. And the reason I don't have a graph with an XY axes on here is because it doesn't make sense to have a negative number of tickets. But what I do need to do on this graph is I need to label my axes. So X is the number of ride tickets. And Y is the number of game tickets. And I need to put some numbers on my scale. I'm going to have both of them start at 0. And I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, depending on your situation, you might want to use a different scale. You don't always have to go by ones, so just make sure you're consistent in your scale, whatever that is. Graph the equation. So our x-intercept was at 4 when we don't have any game tickets, and our y-intercept was at 8 when we didn't have any ride tickets. And I'm just going to use a segment, no arrows on it, because again, we can't have any negative numbers of tickets. So that's our graph. And actually, does it make sense to have it be continuous? If we think about it, can we have a partial ticket? Most likely not, but I'm going to go ahead and leave that line on there. So we've graphed the line, but we now need to find 4 possible solutions in the context of the situation. So here's where we really need to think about, does it make sense to have that continuous line? So we graph the line, but can I have half of a ticket? Most likely not. So when I have 1 ride ticket, I can have 6 game tickets. When I have 2 ride tickets, I can have 4 game tickets. When I have 3 ride tickets, I can have 2 game tickets. So I have a total of 1, 2, 3, 4, 5 solutions on here. My directions are asking to name 4 of them. So I can say 0 ride tickets, 8 game tickets, 1 ride ticket, and we said 6 game tickets, 2 ride tickets, and 4 game tickets, and then 3 ride tickets, and 2 game tickets. That gives me 4 of them. A 5th one would be the x-intercept. 4 ride tickets, 0 game tickets. But the directions don't ask for it, so I'm not going to write it. And here is our example of using x and y intercepts in a application problem.